Hello everyone, I'm Paul and today we're solving problem 611, valid triangle number. This is a medium one that might seem tricky, so next I will show you how to solve this step by step. We are given an integer array such as this one, where each element represents the side of a triangle. And our job is to return the number of triplets, meaning the number of triangles that we can form with these sides. Every triangle has three different sides. We can call this A, B, and C. And the general rule for a valid triangle is that A plus B is greater than C, B plus C is greater than A, and A plus C is greater than B. Okay, so this is required for any valid triangle. And my first intuition here was to use 3 pointers, I, j, and k, to try every possible triplet, meaning every triangle. And whenever I find this, meaning whenever I find a valid triangle, I can add 1 to the result and that's it. The problem is down here in the constraints. We know that nums.length is smaller or equal to 1000. And if we use 3 pointers, we are solving this in n cube. So this solution is fine, but it's very inefficient. We need to think about something else, something more efficient. And the trick here is the following. First, we can sort this. So the sorted array will be the following. And now, instead of trying every possible triplet, we can have an I pointer here at index 0, a k pointer here in the last index, and the j pointer here at k minus 1. And we are trying a triangle with these three sides, 2, 4, and 5. And now the question is if 2 plus 4 is greater than 5. And 2 plus 4 is 6, and this is greater than 5. So this means that this is a valid triangle. Now remember that this is sorted, so if this is true, meaning if this plus this is greater than this value, which is greater than these two, well, of course that this plus this is greater than this, and of course that this plus this is greater than this. Okay, so just by checking this, we are checking all three conditions. And just with this, we have even more information. This means that this triangle is valid, and this also means that 3, 4, and 5 is also valid, and 3, 4, and 5 with this 3 is also valid. So we only had to check this to know that we had 3 valid triangles here. So we can add 3 to the result at this point. And we don't even need to check these values. Just with this information, we know that these 3 triangles are valid, because we know that these values are greater than this one. So if this one plus 4, which is this, is greater than the corresponding value at k, we know that every value in between plus j will also be greater than k. So we can add j minus I triangles to the result. Here j is 3, I is 0, so we are adding 3 minus 0 triangles to the result. That's why here we have a 3. So k is fixed here in the last index. And now the question is, should we move I one step to the right or j one step to the left? Let's see what happens here. If we decide to move j, we are decreasing this part of the formula. And if we decide to move I one step to the right, we are increasing this part of the formula. So we have already tried this, and this was a successful case. From this, we got 3 triangles. So now we want to try to get more triangles with this I. So we can move j one step to the left. So now j is here and we are checking if 2 plus 3 is greater than 5. and this is equal to 5, so this is not true. So we don't add anything to our result, and now we can increase this sum, because if we move J one step to the left, we will decrease this even more, but this is already not greater than 5, so we should increase this. And how can we increase this? Well, we can move I one step to the right. So now I is here, and 3 plus 3 is greater than 5. And this means that here we have another valid triangle. And how many triangles are we adding to the result? Well, we are adding J minus I triangles. This is index 0, this is 1, and this is 2. So we are adding 2 minus 1 triangles, which is 1. So this is now 4. And now we can update K and repeat the exact same process. So we are trying this triangle, meaning we are checking if 2 plus 3 is greater than 4. And this is true. 2 plus 3 is 5. So we know that this is a valid triangle, and we also know that this is a valid triangle. So we are adding, this is index 0, 1, 2. We are adding 2 minus 0 triangles to the result. This is now 6. And now we want to try to move this shape pointer one step to the left and see if we have more triangles with this I. So now J is here, and 2 plus 3 is greater than 4. So here we can add another triangle here. We are adding 1 minus 0 triangles. This is now 7. And what this means is this triangle is also valid. Finally, we can update K, and we are checking if this is a valid triangle, and 2 plus 3 is greater than 3. So here we have another valid triangle, so we add 1 minus 0 triangles to the result. This is 8. And finally, we can return 8. So this is it for the approach. Now with this in mind, let's go with the code, and hopefully you will get the idea. First, we need to sort nums, so nums.sort, and n is the length of nums, and the result is 0. And now for k in range, we start from the last index and we go all the way to index 2, and actually this is non-inclusive, so here we use 1, and we are using 1 because we need to fit both I and J pointers to the left of k, and we are moving in steps of -1. So k will always start at J will always start at k -1, and I will start at 0. And while I is more than J, we are trying the current triangle every time. So if nums I plus nums J is greater than nums k, we have a valid triangle, meaning we need to add to the result J minus I triangles, and we move the J pointer one step to the left, so J minus equal 1. Else, this means that this is not true, so we need to increase this side of the argument, meaning we need to move the I pointer one step to the right, so else I plus equal 1. And finally, we can just return result. So this is it for the code. I think this is right. Now let's submit this and see if it works. As you can see, this works and it's very efficient. Here time complexity will be big O of n square, and space complexity will be big O of 1 or big O of n if you consider sorting. So this is it for this problem. If you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.